We've covered hypothesis testing in a previous module. Now, we will discuss a related topic that is highly relevant to statistical practice that, at least in my opinion, is not emphasized enough. It is known as the multiple testing problem. We begin by defining a form of error that may occur when performing any hypothesis test. A type 1 error, also known as a false positive, occurs when a null hypothesis that is actually true gets rejected. Recall that in a hypothesis test, a null hypothesis states that a population parameter equals a specified value. For example, it may be proposed that the mean weight of apples harvested from an orchard is equal to 200 grams. A type 1 error occurs when the mean weight of the apple population actually is 200 grams, but we rejected that hypothesis in favor of an alternative one. Another type of error is a type 2 error, which happens when a false null hypothesis is not rejected. This is also known as a false negative. In the case of the apple orchard, a type 2 error occurs when the mean weight of the apple population is not 200 grams, but for some reason, we did not reject the claim that it was. Now, in general, type 1 errors are considered more consequential than type 2 errors. As an extreme example, imagine a skydiver who pulls the parachute cord and feels a jolt as if the parachute has opened. Suppose, though, that the parachute has not fully deployed and only partially opened. Here, the skydiver's perception of the parachute opening constitutes a hypothesis test. The null hypothesis is that the parachute has not opened successfully. If they reject the null hypothesis and assume the parachute has opened, when in fact it hasn't, then a type 1 error is made. That is, a false positive occurs, believing that the parachute is in place when it isn't. In this case, the type 1 error may have severe consequences and could possibly lead to injury or death. Now let's consider what a type 2 error would be in the case of the skydiver. If they do not reject the null hypothesis, meaning that they conclude that the parachute hasn't opened successfully, when in fact it has, there's a false negative that occurs. Here, a type 2 error may be frustrating, but has much less severe consequences. It would be ideal if we could minimize both type 1 and type 2 errors. But when one has a fixed sample size, that's usually not possible. Decreasing one type of error tends to increase the other. Though there are exceptions, it's generally the case that type 1 errors, false positives, are more serious than type 2 errors, false negatives. So, what we do is fix the probability of a type 1 error at an acceptable level when performing a hypothesis test. Now, we've already come across this value. The probability of a type 1 error in a hypothesis test is called the level of significance, and it is generally denoted by alpha. Now, one last note before we move on. We've seen that rejecting a true null hypothesis is a type 1 error, and failing to reject a false null hypothesis is a type 2 error. What about the other possibilities, rejecting a false null hypothesis or failing to reject a true one? Well, think about it. Those are both correct decisions. In general, we want to reject hypotheses that turn out to be false, and we don't want to reject ones that turn out to be true. So as far as formally defined errors go, type 1 and type 2 are generally it. Now let's move on to the multiple testing problem. I'll start with an example. According to a recent Centers of Disease Control and Prevention study, the nationwide rate of new cancer cases in a recent year was 487 per 100,000 people. Many scientists believe that some of these cancers are caused by exposure to substances in the environment. So how can we determine which environmental substances increase the risk of cancer? One way is to measure cancer rates in various local regions. Some regions, known as hotspots, turn out to have cancer rates that are significantly larger than the nationwide rate. When a hotspot is discovered, scientists can investigate the environmental conditions there to try to find possible cancer-causing agents. A natural way to discover hotspots is through hypothesis testing. It would seem then that a good way to proceed would be to perform the hypothesis test on a large number of regions, then look for cancer-causing agents in those whose rates are significantly higher than the nationwide rate. Unfortunately, this approach doesn't work very well. The reason is because of a phenomenon known as the multiple testing problem. The multiple testing problem is this. As more hypothesis tests are performed, small p-values become less meaningful. Let's suppose that 20 cities are chosen, and the cancer rates are measured in each. Because we are interested in determining the cities in which the rate is above the national average of 487, we perform in each city a test of the hypotheses. H0 is that mu equals 487, and H1 is that mu is greater than 487. We will use a significance level of alpha equals 0.05, so we will reject H0 whenever p is less than or equal to 0.05. Now, suppose that in 19 of the 20 cities, the p-value is greater than 0.05, so H0 is not rejected. But for one city, p is less than or equal to 0.05. It might seem reasonable to conclude that this city has a cancer rate that is above the nationwide average. However, this conclusion is not justified. Let's pick this apart a little bit. At a significance level of 0.05, the probability of mistakenly rejecting the null hypothesis, thus concluding that the cancer rate is above the nationwide average, is 0.05, which equals 1 over 20. Therefore, we expect, on the average, that out of every 20 true null hypotheses, one will be mistakenly rejected. It is quite possible that all of the cities, including the one for which H0 was rejected, have mean rates equal to 487. The multiple testing problem may potentially occur in a variety of situations. For example, in genome-wide association studies, hundreds of thousands of genetic markers for association with a particular trait are tested. In high-throughput drug screening, many compounds may be tested for potential therapeutic effects. In ecological studies, multiple hypotheses may be tested about the relationships between species or environmental factors. Researchers may test the expression of thousands of proteins in a particular tissue. Differences in activity may be tested across multiple regions of the brain in response to a stimulus. The effects of pollutants or environmental stressors may be tested on multiple species. Basically, any time that multiple tests are performed, there is an increased potential for false positives. So you may ask, how do we deal with the multiple testing problem? Well, the answer is straightforward. We multiply each p-value obtained by the number of tests performed. If the p-values remain small after the adjustment, then it is reasonable to reject the null hypothesis. This procedure is called the Bonferroni method. Let's go back to the cancer rate example. Suppose that 4 cities are tested to determine whether their cancer rates are above 487 per 100,000 people. The results of the test are as follows. City A had a p-value of 0.37. City B had a p-value of 0.41. City C had a p-value of 0.005. And City D had a p-value of 0.21. Here we see that City C may be singled out as a hotspot, but we know that the p-value of 0.005 is somewhat unreliable because several tests have been performed. City C's p-value with the Bonferroni adjustment, however, is p equals 4 times 0.005, which equals 0.02, which is still reasonably strong evidence that it may be a hotspot. In general practice, the Bonferroni method provides a way of dealing with multiple tests. When a Bonferroni adjusted p-value is small enough to reject the null hypothesis, we can be confident in the conclusion. When the Bonferroni adjusted p-value is too large to reject the null hypothesis, yet the original p-value is small, often the best practice is to retest the hypothesis that appears to be false, using data from a new experiment. If, after running a single test, the p-value remains small, then this provides real evidence against the null hypothesis, without the complications that come from multiple testing. Unfortunately, multiple tests are sometimes used to manipulate outcomes in a practice known as p-hacking. P-hacking refers to the practice of either performing a test multiple times until the desired outcome is reached, or testing a large number of variables and only reporting those that appear significant. In a survey of 390 biostatisticians, 40 stated that they had been pressured in the past 5 years not to properly adjust p-values after performing multiple tests to make the results appear more impressive than they were. In the same survey, 20 biostatisticians stated that they had been pressured to change secondary outcomes resulting from testing a large number of variables to primary outcomes of the study. So let's imagine a less than honest pharmaceutical company that would like to show that a new weight loss drug is effective. The company performs a hypothesis test that the mean weight loss of subjects taking the drug is greater than 0. So the null hypothesis is h0 mu equals 0 and the alternate is h1 mu is greater than 0. Suppose that they gather a sample and run the test. Yet, the p-value is too large to reject the null hypothesis. That is, the evidence isn't strong enough to conclude that there is a positive weight loss. It is conceivable that the company may select another sample and rerun the test. In fact, they may do this over and over until they stumble upon an instance where the null hypothesis is rejected. If that last test is all that they report, then they are engaging in p-hacking. They would be able to show data that backs up their desired claim, but by not reporting the multiple testing, they are manipulating the results. Let's click over into R to simulate this last example. I'm going to load the one-sample t-test function that was used in the last module. Now I've created a new function called p-hack that will generate a sample with a given mean, sample standard deviation, and sample size. And it will perform the t-test over and over until a p-value that is less than the level of significance, alpha, is obtained. Let's suppose that the weight loss drug actually does work. Perhaps the sample shows a weight loss of, say, 1.2 pounds, with a standard deviation of 0.8 and a sample size of 40. When we run the p-hack function with a null mean of 0, it returns a very small p-value. Note that it only took one run of the test to obtain that p-value. Note also that there really is no Bonferroni adjustment, since there's only one test that was run. Suppose now, however, that the weight loss drug doesn't actually work. Here, say that the sample shows a weight loss of 0, which is the same value appearing in the null hypothesis. We would expect that since the sample mean and the null mean are the same, that we would get a large p-value, and that the null hypothesis would not be rejected. Let's run the p-hack function. In this instance, we obtain a p-value of 0.0342, but it took 6 tests to get it. Now, the company could report only this last p-value and provide the data from the sample as evidence that the drug works. What they should do, however, is stop being so shady, or at least report the Bonferroni adjusted p-value, which is 0.2054. Note that with the Bonferroni adjusted p-value, we would not reject the null hypothesis, much to the disappointment of this sketchy pharmaceutical company. There are lots of other ways to manipulate data, including just changing data values in favor of the desired result. But p-hacking is real, and certainly happens more than it should.